Hello everyone, we are excited to present our work OPPerTune, Post-Deployment Configuration Tuning of Services Made Easy. The application configuration plays a crucial role in determining its performance. While a good configuration can improve the app's performance, a bad one can make it significantly worse. For example, while benchmarking a microservice-based cloud application, we observed that while good configurations improved the P95 latency by up to 40%, a bad configuration increased the P95 latency by about 100x. Considering the impact of configuration tuning on application's performance, we'll look at how to find the optimal configuration to maximize performance while the application is deployed in production. An important challenge in tuning services is the large configuration space. Let's consider the example of a cloud application implemented using microservices architecture. For simplicity, if we assume there are n microservices, each with p parameters, and each parameter can take c values, then the total possible configurations is c to the power n times p. Such large configuration space makes an exhaustive search infeasible. So, how to find optimal configuration in minimum steps? Well, configuration tuning is an important problem and classical problem that both ML and systems groups have been working on, including our group. Consider self-tune, which is a state-of-the-art tuning algorithm from our group published at NSDI 2023. Even though it addresses some aspects not covered by other solutions, we realized from our discussions with the product groups that it still doesn't address crucial problems related to tuning cloud services in production systems, such as filtering important parameters to tune from a large set of parameters, handling numerical and categorical parameters, etc. We therefore introduce OPPerTune, which addresses all these problems. Let's look at the high-level idea of how an application can use OPPerTune to tune its parameters. We will look at the internal components of OPPerTune in later slides. The application, which is in deployment, asks OPPerTune to suggest parameters that it believes will provide the best performance. OPPerTune suggests values for each of the application's parameters. The application reconfigures itself to use these suggested values. It also keeps track of how the metrics evolve over time while it is running with this new configuration. Once the metrics have stabilized, the application provides feedback to OPPerTune by telling if the suggested parameter values were good or bad, which OPPerTune uses to learn and provide even better values in the next iteration. This process repeats till an optimal configuration is found. Note that there's an initial one-time setup that the app needs to do where it tells OPPerTune which parameters to tune, which algorithm to use, which I did not show here for brevity. Now let's look at the process in more detail. Let's consider a single application whose parameters we want to tune. Let's say there's a metrics monitor that is tracking the application. Metrics such as throughput, latency, etc., which is likely true for any production grade application. To help improve the application's configuration, let's say there's an instance of a tuning solution on the OPPerTune server which caters specifically to this particular application. We call this a tuning instance. Each tuning instance contains the parameters of its application to tune, the algorithm to use for tuning, and the internal state of the algorithm to maintain the tuning progress. The application asks its tuning instance for the parameters it believes will maximize the application's performance using the predict interface exposed by the service, OPPerTune service. The tuning instance responds with the new parameter values. Notice that there are several parameters that are being tuned simultaneously. Moreover, the parameters are of different types. For example, here we see integer, real, and categorical parameters. The application takes these parameters, reconfigures its components with these new values, and runs for a while, which may vary from a few minutes to a few days. The metric monitor continues to observe the application metrics in the background. Finally, when the metrics have stabilized, they are fed to the reward function. The reward function should use the metrics to produce a single real number, which is the reward value. And this reward value quantifies how good or bad the parameters suggested by the tuning instances were. This reward value is now sent as feedback to the algorithm using the setReward interface of the OPPerTune service. OPPerTune uses this reward to learn and suggest even better values in the next iteration. The algorithm uses this reward to update its internal state. The entire process that I went through now is called a single tuning iteration. The application will go through several such iterations to optimize its performance. We just talked about a single user, single application, single tuning instance scenario. But in reality, there will be multiple users of the OPPerTune service, each with one or more applications to tune, as you can see here. Also, each application will in turn have a tuning instance assigned to it, and multiple applications may also get tuned by a common tuning instance. Karan will now discuss how OPPerTune addresses various challenges in post-deployment configuration tuning.
Thanks, Gagan. Let's now move on to the first core challenge of tuning configuration parameters, which is handling hybrid parameter spaces. We just saw that apps can have a mix of numerical and categorical parameters. As we will demonstrate later, these parameters need to be jointly tuned in order to achieve optimal app performance. There are several aspects of this problem that make existing algorithms ineffective. First, the lack of a notion of continuity in categorical parameters makes gradient-based algorithms inapplicable. Second, traditional bandit algorithms and deep RL techniques somewhat handle the hybrid parameter space but take too long to converge to the optimal parameter values. Third, the Bayesian optimization-based methods are inapplicable because they assume that the reward function is static and can be queried multiple times at the same value. This is not possible in production due to the dynamic workloads. We propose a novel algorithm called hybrid bandits that jointly tunes both numerical and categorical parameters and scales linearly with the number of numerical parameters and total categorical combinations. It uses a combination of two algorithms, one for tuning numerical parameters and another for categorical parameters. For the numerical parameters, it uses a derivative-free pseudo-gradient ascent-based approach and approximates the gradient of the reward function. In essence, it perturbs the parameter value in one direction by a small amount, delta, and then in the opposite direction. It receives a reward from the application for both these perturbations. It then uses an update rule to move in the direction of the increasing gradient. Note that we use gradient ascent since we want to maximize the reward. For tuning categorical parameters, hybrid bandits uses a multi-arm bandit algorithm. Let's say we have two categorical parameters, parameter A, which takes values A1 or A2, and parameter B, which takes value B1, B2, or B3. In total, we have 6 possible combinations for these two parameters as shown. Initially, all combinations are said to be equally likely to be chosen by the algorithm. Let's say the combination A1, B3 is chosen by the algorithm. These values are sent to the app as the prediction. Let's assume the app uses these values and gives back a high reward, which indicates that these values were good. The algorithm then uses an update rule to increase the probability of this combination getting selected in the future. Let's say in the next iteration, some other combination A2, B2 is chosen. Again, the app uses these values, but this time sends back a low reward, since this configuration was possibly bad. The algorithm decreases the probability of this combination getting selected in the future, and this process repeats. Note that the algorithm has been somewhat simplified to provide intuition. For complete details, we encourage you to look at the paper. But the major challenge is how do we combine these two algorithms, since A, they tune completely different types of parameters, and B, they need to work with a common reward value, which was given by the user for the overall parameter, the overall prediction of the parameter values. The details on how we address these challenges can be found in the paper. We evaluate the effectiveness of hybrid bandits on the Death Star Ben's social network app in one of our experiments. Just to give context, the social network app has 28 microservices that together implement several features of real-world social network applications. The constituent microservices include Nginx, Memcache, MongoDB, Redis, as well as microservices that implement the logic of the application, each of which has numerous parameters of different types. All these things make the social network app a good benchmark for our experiments. The workload involves sending a large number of GET and POST requests to the app at different rates ranging from 2,000 requests per second up to 3,600 requests per second. The metric of concern here is the mean P95 request latency. We run each algorithm shown here for 50 iterations and report the mean and standard deviation for the converged configuration values over 5 trials. In each plot, the y-axis represents the mean P95 latency in milliseconds, and the x-axis represents the tuning approach used. The black line on top of each of the bars represents the standard deviation of the P95 latency. The key takeaway is that hybrid bandit outperforms all other algorithms in each scenario, and especially so at higher workloads. This also highlights the importance of tuning both numerical and categorical parameters. Next, we discuss the second challenge, which is how do we scope the tuning problem when there is additional information about the workload, the infrastructure such as the machine type, etc. available. But what do I even mean by scoping? So let's consider a scenario where a service operator is managing an app that runs on 10 different clusters. The operator now needs to decide whether just one shared tuning instance amongst all these 10 application deployments will suffice for tuning, or if there is a need to create one tuning instance for each of the 10 clusters, based on how much the workload varies amongst these clusters. This is what we refer to as scoping, and it is not an easy problem. Therefore, we introduce an algorithm that the operator can rely on to automatically do the scoping for them. For example, consider that now OPPerTune is provided with some information or context regarding A, the workload size, which can be small, medium, or large, based on how the app operator defines these, and B, the cluster ID, which represents the cluster in which the workload will be assigned to. Different clusters can have different hardware, operating system version, etc., which can affect the optimal choice of these app parameters. In this example, there are 2 copies of the same application running on 2 different clusters, both of which handle workloads of different sizes. In total, we have 6 possible combinations for the context space as shown. One extreme could be to have a single tuning instance responsible for all 6 contexts. TI here is short for tuning instance. The other extreme could be to have one specialized tuning instance for each of the contexts. The first setup effectively does not utilize the provided context and thus may provide suboptimal predictions for certain contexts. The second setup utilizes the context well, but becomes sample inefficient since now we have to train 6 tuning instances. Can we have something that sits between in these 2 extremes? An intuition for such a solution is that in the second setup on the right, it is quite likely that there are groups of contexts that have roughly the same optimal configuration and thus can be tuned by a single tuning instance. We thus propose a novel decision tree-based scoping algorithm called AutoScope that automatically determines the right scope of tuning instances. As we will see in the next few slides, this approach utilizes the context well and is also sample efficient. With this ability, the app can now provide additional information while asking for parameter values from OPPerTune, such as the workload and the environment. Let's look at a simplified representation of the algorithm. On the right-hand side, we also show the code equivalent of the scoping model learned by the algorithm internally. Let's say there is an incoming workload, which is a large workload and will be assigned to cluster 1. The algorithm uses this information to find the tuning instance best suited for tuning parameters for this context, in this case tuning instance 2. If another workload arrives, say with a different context, the algorithm finds the best suited tuning instance for it, which in this case is different from the tuning instance chosen for the previous context. Once the reward is collected, the algorithm uses it to update the tuning instance at the leaf and the scoping model by updating the weights along the root to leaf path. We evaluate autoscope in one of Microsoft's large ML experimentation pipeline that uses Apache Spark to prepare data before training various ML models. We tune Apache Spark parameters with the goal of minimizing average job completion time. The context variables available to us for this workload were the job type, the dataset size, and the cluster ID. In total, we had 44 possible contexts. We provide comparison with 3 techniques, the details of which can be found in the paper. The key takeaway is that remarkably, Autoscope uses much fewer samples and tuning instances to achieve performance competitive to self-tune, which is a state-of-the-art algorithm, for which we had explicit scoping, that is, one tuning instance for each of the possible contexts. Lastly, we look at the third challenge that OPPerTune helps address, which is filtering the parameters to tune. A service may have like thousands of parameters to tune across its entire stack. If we naively start tuning all of them, it will take quite a while before we converge to the optimal configurations. Moreover, tuning every parameter means when the app is reconfigured, several components of the app may have to be restarted for the updated parameter values to take effect, which can result in service disruptions and thus make tuning costly. We propose a simple yet effective filtering strategy called micro-benchmarking, which helps filter and reduce the number of parameters to tune, and in turn also helps reduce the cost of tuning. So if our app has n parameters where n is quite large, the micro-benchmarking strategy assigns an importance value to each of them. The user can then choose to tune only the top k parameters from this ranked list. In the interest of time, I'll skip the algorithm and experiment details. These can be found in the paper. The key takeaway from our evaluation is that micro-benchmarking is indeed effective and achieves a good trade-off between performance and the cost of tuning. In this particular evaluation, cost refers to the number of microservice pod restarts. To summarize, parameter tuning for deployed apps is hard for several reasons, such as the large parameter search to space, the hybrid nature of parameters, determining the right scope for tuning and utilizing the context information, deciding the right subset of parameters to tune, and more. OPPerTune helps address all these. To do so, we propose novel algorithms that tackle these challenges and build a general end-to-end tuning service which is scalable, easy to use, and has been open source. This concludes the talk. We would like to take this opportunity to highlight that the systems innovation group at Microsoft Research is always on the lookout for motivated candidates for researcher, postdoc, and internship positions to work on cutting-edge research at the intersection of AI and systems. Please check out our work using the links provided here, and feel free to reach out to us using the email ID. We welcome you all to try OPPerTune. If you're interested in this space, please reach out to any of the authors. Thank you.